Okay, now I know this looks scary, but it's really not as bad as you think. This is a lot of symbols, but we're going to work through it pretty darn quickly, but easily. Up here at the top, we have H equals U plus PV. This is just the definition of enthalpy. Okay, enthalpy is represented by H. It's always fairly difficult to think of a good way to describe these things, to define them in words, especially since they are so very thoroughly mathy. But I'm going to not even try this time. We'll eventually get to what enthalpy is. For now, just try not to cry and let's run with it. Okay, so H equals U plus PV. That is to say, H is equal to the internal energy of the system plus the pressure of the system times the volume of the system. This is fairly abstract. Yeah, we're getting kind of weird here, but that's the thing about physical chemistry and thermodynamics. You can play some weird tricks and get to some really interesting conclusions. So let's just stick with it for now and just accept that because these are all state functions, U, P, and V, that means that H, enthalpy, is a state function. So that lets us take advantage of some things. Now, we also already know that internal energy, or the change in internal energy, is equal to Q plus W, heat plus work, which means that it's equal to Q minus P delta V, because we already know that work is equal to negative P delta V. All right. So we just rearrange that a little bit. We add P delta V to both sides. We get Q equals delta U plus P delta V. We are almost done. We're still working on it. But all we have to do now is go back to the original. We have H equals U plus PV. Well, that means that delta H equals delta U plus P delta V, and Q is equal to delta U plus P delta V. And delta H equals Q. In other words, enthalpy, or the change in enthalpy, is just the heat that you've added to the system. All of a sudden, we have a state function that is really easy to measure. We've gotten it down to a single term, Q, heat. But you'll notice over here at the right, I have written that this is only true at constant pressure. That's because I kind of elided a little bit of a shortcut. When I say delta H equals delta U plus, that should be delta PV. Okay, you have to basically track the change in PV as it follows the path, because ordinarily that's a path-dependent function. But if you just say that this is occurring at constant pressure, you get to bring the P outside of the delta, it becomes P delta V, everything suddenly becomes super duper simple. But it means that enthalpy is equal to heat, it's equal to Q, only for a limited range of, or a limited set of experimental values. That means it's only true when pressure is constant. But that means that it's true for the majority of chemistry, because constant pressure just means that it's open to the atmosphere. The pressure is constantly in equilibrium with the air around it, so pressure doesn't change. So for, benchtop chemistry, laboratory chemistry, like you have been doing, like you're going to do for the rest of your life, whether you set foot in another chemistry classroom or not, delta H equals Q. Q becomes a state function at constant pressure. Okay. That is the takeaway here. At constant pressure, Q becomes a state function, and everything becomes much, much easier. And that really is why we use enthalpy, because it makes things so much simpler, so much easier. It's a state function. All you have to do is track the state of the system. It ignores work. Work is nasty and stupid. I hate work. Yes, I did mean that in all the senses. And focusing on heat means you only have to focus on the one thing, and that means all you need is a thermometer. Because it's constant pressure, it focuses on the simple laboratory work you're likely to see, and that means all you need is a thermometer. You put a thermometer in the thing, you start the reaction, you wait until it's done, you measure the temperature before and after, you're done. Okay, that's not entirely true. You need to be a little bit more careful than that if you want to do your work well, if you want to get good results. And frankly, my work in grad school was basically temperature before, after, and so on. And we used $25,000 pieces of equipment. But the principle is the same. It makes it better and easier, and I like better and easy and simple, and that's why we use enthalpy. So what that boils down to is that you can think of enthalpy as just being the energy released or absorbed during a change of state. So for example, the enthalpy of a reaction is the energy released by a reaction or the energy absorbed by a reaction. Okay. So you look at this top one here. Water going from a solid to a liquid. Water is melting. Delta H is positive, 6.01 kilojoules per mole. It's pretty simple, pretty straightforward. What that means is that you have to put in 6.01 kilojoules of energy to melt 1 mole of water. So about 18 grams of water requires 6.01 kilojoules. So that's one of the things to take away. We're still using the same sign conventions. Positive means that energy is going into the system under consideration. Negative means energy is coming out of the system under consideration. Is that a lot of energy? Is it a small amount of energy? It's still kind of abstruse, a little bit abstract, a little bit hard to nail down in terms of real terms. But it's fairly high compared to other things, smaller than some others. Now we come down to the bottom, and instead of looking at changing from a solid to a liquid, we're actually looking at the formation of water. If you combine 2 moles of hydrogen and 1 mole of oxygen, you're going to get 2 moles of water. And it's also going to release a heck of a lot of energy. That delta H right there is negative 241.8 kilojoules per mole. Okay. Think about holding 18 grams of ice in your hand and melting it. That's a heck of a lot of ice, and it would hurt like hell. Now imagine exploding 18 grams of water and realizing that it's releasing 40 times that amount of energy. That's why you don't hold a firecracker in your hand. Explosions are big. They're bad news, and you want to be careful about them. And again, we see the sign convention. Negative means that it's releasing energy. The hydrogen and the oxygen have a lot of chemical potential energy. They transform, they shed some bonds, gain some others, and they release a lot of energy in the form of heat, and boom. That is an exothermic reaction. So exothermic means releasing energy, endothermic means absorbing energy. So solid transforming to a liquid is an endothermic reaction. Liquid turning to a gas, boiling, is an endothermic reaction. And of course, the opposite is the opposite. So liquid turning to solid is an exothermic reaction. And that causes some people trouble. They think of exothermic as being hot, but exothermic means it's releasing energy. And when a liquid turns to a solid, it's losing kinetic energy. The molecules, the particles, what have you, are slowing down, and that kinetic energy is being released into the surroundings. So the surroundings are really damn cold, and the surroundings are taking energy from water, and that's why water freezes in places other than South Carolina. Now, although, as you might have noticed, I have changed over to a new method for recording these, one that I hope will give better audio quality and still make them slightly faster to produce, I'm still going to draw pictures because I like to, darn it, I like playing with the colors, and I'm actually surprisingly fond of my handwriting. So here we have solid, liquid, and gas, and going from solid to liquid to gas is an endothermic process. Okay? Going from gas to liquid to solid is an exothermic process. For those of you who are very pictorially minded, I recommend you come up with something to help you remember that. Becoming more solid, becoming more still is an exothermic process because you're releasing energy to your surroundings. Becoming faster, hotter, less dense is an endothermic process because you need to take in energy from your surroundings in order for that to happen. Now, you need to be careful about delta H of reaction because the delta H of reaction is the enthalpy per unit of reaction for every time the reaction occurs. So the enthalpy of reaction for the formation of water is negative 241.8 kilojoules per mole. What that means is per stoichiometric equivalent moles. So per 2 moles of hydrogen, per 1 mole of oxygen, per 2 moles of water. So if you have only 1 mole of hydrogen, then that means that it's only going to produce 120.9 kilojoules of energy. Let me go ahead and write that out for you. Still working with our water reaction, how much energy would be liberated by blowing the hell out of 5 grams of hydrogen? Well, all roads lead to mole. So the first thing you're going to have to do is convert to moles. So 5 grams of hydrogen times 1 mole per 2.016 grams. Grams of hydrogen cancels out, leaving us with 2.48 moles of hydrogen. Now, the question was, how much energy will be produced by 2.48 moles of hydrogen? You need to answer that question using the delta H of reaction, which, as you might recall, was 241.8 kilojoules per mole. Negative 241.8 kilojoules per mole. But per mole of what? That's per mole of reaction, which means stoichiometry time for every 2 moles of hydrogen, which produces about 300 kilojoules of energy. Not, kilojoules per anything, just 300 kilojoules of energy. That's how much is liberated by burning 5 grams of hydrogen. It's vitally important that you never, ever, ever forget that stoichiometry. Those 2 moles of hydrogen down there in the bottom, that makes a really big difference. You need to remember that. You need to remember that this delta H of reaction is per unit of reaction, and that the stoichiometry of each individual element is going to change how much energy is released or consumed by any particular reaction when you're considering it in terms of that individual, not necessarily element, but reactant or product. Never forget that. It will screw you up if you do, and you'll die cold and lonely in the rain. All right, we're staring at about 15 minutes, so let's go ahead and take a quick break here. Call this the end of video 3, I think it is. And when we come back, we will continue our discussion of thermodynamics by going into calorimetry.